Morning, guys. This is the lecture on, or the beginning of molecular geometry for AP Chemistry. So, in your notes, past when we started doing the Lewis dots, and this is building on Lewis dots. Lewis dot is essential in order for you to be able to figure out the geometry, because it comes from how many pairs are involved in a bond, how many domains, which means how many locations of electrons are there around an atom, and then how many electrons are not binding, or they call them a non-bonding pair, a lone pair. So this all starts on page 13 in your notes. So when we talk about molecular geometry comes from what's called the VSEPR model. And the VSEPR model comes from valence shell electron pair repulsion theory, VSEPR, and they say VSEPR. It's a lot of acronyms in chem, and chemists don't really care for English. So when you look at this repulsion theory, because you're looking at electrons in space, you're looking at the best three-dimensional arrangement to give those electrons the most space to move and minimize the amount of times they come close enough to each other to get a significant repulsion. You will always have a repulsion because it's negative with negative, but you're minimizing how much repulsion is there, and you're trying to keep the molecule as stable as possible. Okay, so it really starts with the thought that the atoms really want to be as far apart as possible, giving each atom the space that it wants for its electrons and the shared electrons that go between them. And when you do this, you do the Lewis dot, and then you look at these things which are called electron domains. Okay, so that's where it comes from. So the electron domain is determined, again, by the Lewis dot. Let me get my little gloves on so every time I touch the screen it doesn't move it. All right. So this is depending on our Lewis dot. And that's why, the past few days we've been practicing Lewis dot. We're going to do it some more, and then we're going to take it further. We're going to look at the Lewis dot that you have, and then we're going to justify its shape. Okay, there's certain Lewis dots you must have committed either to memory or be able to draw with confidence when you have a molecule. So remember, those are carbon with 4 things attached, whatever the 4 things are. You definitely should be able to draw nitrogen's Lewis dot, oxygen's Lewis dot, any type of halogen. So I'm going to use X here. That's a diatomic. Okay, that's a halogen. The tricky ones, carbon dioxide. Okay, that's one that you absolutely need to know, and we're going to go through that one because that one falls into one of the domains we're going to talk about. So remember, a domain is a space where it can be found. A domain is anywhere where it's a shared area of space or a lone pair. Okay, now you have to be careful because people want to take things like this double bond and call it 2 domains, but that is one domain. It is one shared space. So a domain, again, is a shared space of a bond, whether it's single, double, triple. It is where a lone pair of electrons can be, like on the top of nitrogen there you see a lone pair. It can be a lone individual electron because in some of the situations, nitrogen with oxygen, nitrogen only has 1 electron sitting on top of it, because that's how we do our Lewis dot. Whatever many remaining electrons are, they go on the center atom. So just remember that. Then, because of how these occupy the space, you get what's called a bond angle. And a bond angle tells you the angle between atoms. So I'm just going to use generic here. If I have this bond, this compound, these are generic. I shouldn't use Y because yttrium is an element. This is the bond angle from there to there. That is called a bond angle. It's the bend Oh, I forgot to get that open for you. Hold on for a second, because we're going to go and use it. Right, when we were doing mole view, or mole view actually, because it's molecule view. Right, this is talking about bond angles. So if I wanted a bond angle between here, and I know it tells me where I can get angle, I could say I want the angle between here to here to here, and it tells you it's 122.4 degrees. Okay, so that is one of the things that you can do. And I'm going to take off the angle. Should be out of that, right? Yeah. And I'm going to clear this because we're going to use it in the future to do other drawings. Now, this just definitely determines the overall shape of the molecule, and you have to understand that the shape and the shape and the geometry and what's called a domain, an E-domain, are particular things. So we're going to look at it. The electron pair geometry, and I call it the title of the geometry domain. This is actually called a parent class. This is the E-domain. So when somebody says, what is the electron domain, it means like the big overall parent class that you start with to get your shapes within a certain number of starting domains. Okay? And you might say, well, what do you mean by that? Well, if I have CH4, and this is its Lewis dot, I'm using a line to represent the dots, and that's still okay. I have, and I'm going to change my pen over here, and I'm also going to go a little skinnier on the pen. I have 1, 2, 3, 4 domains. Okay, so we're going to find out that 4 domains, and these are E-domains, how many domains the electrons reside in. That starts a parent class or E-domain class of tetrahedral. 4, tetra. Right? We're going to see if I put this together in mole view. Let's clear this out. Oh, it is cleared. Oh, I should be doing carbon hydrogens. Come on. There we go. Wow, that took me a while. And I go look at the 3 dimensions on this, and I rotate it. That is carbon in the center, and this is a tetrahedral because you have faces. Right? I have a face from here, whoops, here to here to here to here. That's one face. I rotate it. I'm going to grab this and rotate it. Nope, it's not rotating the way I want it to rotate. Hold on. Put it back like this. Okay, here's one face. You're looking at the face. Now, if I rotate this around, here's a second face. So that's face number 2. I'm going to rotate it around, and that's face number 3. And then the other part on the bottom is 4. So it's 4 faces, 4 sides, tetrahedral. And that's where it comes from. That's why I showed you this program, because you can come in here and play to get an idea about the 3 dimensions that everything exists in. Remember when I told you in space, this doesn't just stay in space hanging out like this. It rotates. Whoops, come on you. It rotates around, it moves, it never stays still. It just keeps going, and it floats around in air, moving in all different directions all the time. Okay, now if you lower the temperature, it'll move slower. If you raise it, it moves faster. It has to do with kinetic energy. So keep in mind there's an E-domain. The molecular geometry is the actual shape, because this gives you the shape in reality. So I showed you a tetrahedral because it was 4 domains all bonding. That gives you a tetrahedral. Now, if I were to do another molecule in a similar E domain, which is NH3, we would say we have 3 bonding domains and 1 lone pair, or non-bonding, right? Because here's a bonding domain, bonding domain, bonding domain, 3 bonding. And this is how you justify it, exactly how I'm doing this. 1 non-bonding. Okay, so my E domain is tetrahedral, that's the parent, because I have 4. But its shape is different. Okay, so its shape, and I'm going to see if I can put this together for you, because, again, it's like I have brain farts. I come to do, I'm going to put nitrogen, and then I know this looks weird that I'm just putting 3 nitrogens, but I'm going to change it. I'm going to change those nitrogens to hydrogen by just going to H and say, oh no, now let's make them H's. And then I need a single bond. Oops, there we go. No, this way. Oops. That's me, my fault. See, technically challenged, single bond. Let's just do it this way. 1, 2, 3. Went to the hydrogen. I'll change these 3 to hydrogens. Now you can't draw in the lone pair. This is where the formal charge comes from. Nitrogen has 5 electrons. I have 3 in a bond, so I minus 3, and then I subtract the 2 for the lone pair, and so my charge on nitrogen is 0, so I don't come down and change the charge on nitrogen. I leave it, and then I say, okay, show me my 3-dimension. Whoop, I gotta go over here, 2D to 3D. Okay, so here's my nitrogen. Notice it's a different shape. There's nothing sticking off this side of the nitrogen because it's all lone pairs, and they're taking up the space on top of the molecule. Trying to get it so you can see it the way people normally look at it. You know, this is a tough one. Remember we talked about the planes of symmetry? I can get a plane that cuts through this nitrogen, back through the back hydrogen, and then we'll cut these 2 hydrogens apart so that it's symmetrically looking at each other. Come on and rotate the way I want you to rotate. Oh, we can rotate it back that way. I can't get my little nitrogen to go up. But you can look at it at an angle here. It would cut this way. That would reflect on that. But I can't get one going perpendicular to that horizontally. So I got one vertically, but there's no symmetry because you get the lone pair up here. With lone pair up there, you now have an unbalance of electrons. The electrons actually get pulled into the nitrogen. The lone pair sits up there, doesn't affect the pull, but because there's no effect with that lone pair, we don't have equal and opposite pull. So the nitrogen becomes what's called a trigonal pyramidal, 3-sided pyramid. Okay, and it is asymmetrical, therefore polar. I'll move this up so we get down to these things called bonding pairs, non-bonding pairs. So if we look at what I talked about in terms of bonding, non-bonding, your bonding pairs are anything that's between 2 atoms, anything that makes a bond. All of these, right, are considered a type of a domain. So if I have the double bonded oxygen here to carbon, there's 2 domains. Both of them are double bonds, but each double bond is a domain. When you look at non-bonding pairs or lone electrons, there's stuff that's not in a bond. Very intuitive, go by the words, don't overthink it. Those are all terms that we need to go on and look at shapes. Okay? So we're going to start looking at shapes. Whenever we start looking at these shapes, I'm going to have to open this up twice to talk about it. You go through a series of questions. you always draw the Lewis dot. Okay, first and foremost, you draw a Lewis dot. And guys, when we get done with this, there are certain Lewis dots you're not actually going to have to draw anymore because you've done it so often that you're going to be like, oh, I remember that one. This is going to have so many bonding pairs, so many non-bonding pairs. It's going to be in this domain, and it's going to be this shape. Right? So we have these domains that are based on the number of bonding pairs. If you draw the Lewis dot, then you go back and you look at these following 3 questions. How many total domains do I have in the Lewis dot? Total. How many bonding pairs? I shouldn't say bonding pairs. How many bonding areas and how many non-bonding areas? And then you break it down. So you have a total number and then you count. How many are involved in a bond or are a bonding area? And how many are not in a bonding area? So when I say how many are bonding, how many bonding areas do you have in the molecule? And then how many non-bonding areas, lone pairs? And it could be a lone electron too, so remember that. So as we go through this, and we're going to get to this later. This comes later when we talk about this thing called hybridization. Right now I want you to focus on just geometry and looking at how do I get this. So I'm going to use, and you can do this at home, if you can use the mole view, but I'm going to do this, I'll see if I can get it. I'm using just marshmallows. And normally you guys have the 3-dimensional kits that we have in the classroom, but you're home and you probably don't have those. So if you want to follow along, toothpicks, I'm going to start out with 6 because we go to a domain where there's 6. We're only going to get through 4 tonight on this lecture, and then I'm going to make another lecture that goes through the last 2. So I have a center atom, big marshmallow. You can use other things. You got raisins and yellow raisins and regular raisins. Anything that you can stick. You can use grapes. So you can have 6 grapes on the outside and 1 in the middle. That'll get messy for the one in the middle. But something that you can stick a toothpick into. So when we look at a 2-domain, I've got a center atom, and I have 2 things binding off of it. I might shorten these so that you can see it underneath the ladybug. So I'm just going to break my toothpicks in half because they're really long. I actually use them because they're long enough to go across a beaker, and they hold my chromatography paper for forensics. Hang them just right so the chromatography paper doesn't touch the side of the beaker. So here's my little molecule. There's a really big atom in the middle and 2 little atoms on the outside. I hate this because I always get reflection. Does that work? Maybe it'll work. A little bit. And we have our little molecule there. Okay. Now notice that 2 domains, no lone pairs, it is going to be linear. So when we have 2 domains, no non-bonding, we are in a 2-domain E domain. That parent name is linear. And the only structure you can have is this thing called AB2. Right? I have a center atom, and then I have 1 on either side. So if I draw it, it looks like this. Center atom with 1 on either side. You can also have a double bond. That's also what you'll see. The bond angle between these are 180 degrees because it's a line. And then here is an example. Beryllium chloride. Remember, beryllium is the exception to the octet. So we total up our electrons, keeping in mind beryllium is the exception to the octet. And you have beryllium in the center, a chlorine on either side. You have equal opposite pull. That's what these arrows are. I have a pull from the chlorine this direction, and it's a dipole and it goes that way, and then a pole this way, goes this way, and then you have the equal and opposite pole, so there's no net pull, no net flow. No net pull, no net flow of electrons is non-polar. So think the word no movement of the electrons, no flow of the electrons. There's a no in non-polar. Okay. The other one you'll see is CO2. When you go through and do the Lewis dot, which you're doing this weekend, and so you can check your answer, and you have to try to do it by yourself. I know right now our tests have to be open book, open note, because we have the mixture of remote and not remote. You have to be able to do all of this by yourself. You've got to try to say, I don't have that material. And when you go to do the part 2s and you're timed, it's going to get to a point where you've got to go fast enough that you're not looking anything up. So that'll be linear. 2 bonding, 0 non-bonding. Remember, we're talking about central atom, not the oxygens, the central atom. 2 bonding pairs, 0 non-bonding. And remember, I put a line through my 0 to keep it straight from whether it's a 0 or an oxygen. Now we go to the next size, the next type. And that's why I said, that's what I'll do, guys. I'll switch. Move this up so that all gets on there and we can talk about it. So if we look at this one, now this is the one that we've got that exception to the rule for boron, and boron loves to do this. Now remember, atoms want to be as far apart as possible when they make the structure. So if you were to go into your mole view and say, okay, I'm going to erase this. Now I'm going to do boron bonds. So I have to come back down here to my other periodic table. I'm going to pick boron. I'm going to put boron in the middle. I'm going to do, I had to move up, single bond. I'm going to do 3. And I'm going to change them because I said it was hydrogen. Okay, notice I'm cheating. I make the bond go by default to carbon, then I change the carbon to another atom. Now I'm going to do formal charge on boron. Okay, boron is 3 valence electrons, minus 1, 2, 3. And when we did the Lewis dot, we said there weren't any valence electrons here. 3 bonding, 0 non-bonding. So now I'm going to ask it, because I don't have to change the charge on this. This is going to be a formal charge of 0. I'm going to hit 2d to 3d, and here's boron. Now this is called a trigonal planar. Some people call it trigonal. I call it trigonal. And if I move this, see if you look, all the atoms are in a plane. You can do a mirror symmetry plane right through the center of those atoms, and then you can do one right this way, up and down, right through this, going back into your computer, coming back out of you, and these two reflect on each other. Okay, not sure how that looks? Let's look at it in our little marshmallow model. Here's my marshmallow model, here's my boron. Okay, this bond didn't go in far enough. Okay, they're all single bonds, the bond lengths should all be the same. So here's my model, and I can take my little, I was going to use this. Here's my plane that goes through it like this. And those two atoms, if I was in a perfect world, and I probably should use the model kit so you can see it, but I want you to say, you can do these at home with your little marshmallows. Goes through that way, and then if I tip it up this way, I can have a plane go that way. But that's perpendicular to each other, because this one's going this way, and this one's going that way. So notice, horizontal, vertical. And if you go on to chemistry, there is a whole, like half a semester in what's called inorganic chemistry, where you do symmetry of the molecules, and there's all these different, like there's an S symmetry where it's a point symmetry, where you have your regions of space, and it's symmetrical from up here to down there, but it's not symmetrical anywhere else. So they give it an S symmetry. And then there's a whole bunch of other ones. In fact, I have to go back and look at it because I haven't done it in 40 years. Ooh, that's making me sound old. And 40? 30. Sorry, 32. Yeah, no, it's still making me sound old. Never mind. Okay. So this starts off with the one in the center, and if you look at these bond angles, we're cutting a circle into 3 equal parts, so it's 120 degrees. Do you need to know the bond angles? Yes, you do. Ouch, but yes. But think spatially. You all took geometry, right? You've all even done well, I shouldn't say all, because I think some of you have Algebra 2 in the spring, so that might be a bummer. But you will get to a point where you're even looking at some trig functions, unless they move that all into pre-calc, which is a bummer. Yeah, that's right, I forgot. They did the new math, which is so stupid in New York State, because you need stuff like this, and they just push it off to further. So anyway, getting back to the method at hand, we have 3 bonding pairs in that 0 bond bonding, and it's AB3, and we call it trigonal planar. These two, the top line, this top line in every domain will be the same as the parent name. So remember, this is the E domain, and then these are the actual geometry names. Whoops, don't do that. Okay? So if we take one of these away, so we're just going to remove one. So I'm going to go back and I'm going to change, not that boron would do this, but we're going to look at generically. I'm going to remove one of these, right? And I have to change the formal charge now, because boron has 3 electrons, and now I only have 2 being shared, so I'm going to change its formal charge to +1 in order to get the right shape. And that's not the right shape. Okay. Right, did I do that wrong? 3 valence electrons, -1, -2 should be +1. I'm going to take that away and see what it gives me, because I know what the shape should be, and it is not linear. Nope, it's still done. Oh, because doofus didn't do that. Sometimes I make really silly things. No, it goes back to that, giving you your lone pair here. Hold on. It's supposed to work by formal charge, but it's not. So what could I use? It's probably because it's boron. Can't do that one. I'll do it visually the other way. Let's look at it through our little... Here's our molecule. We're taking 1 bond off. Boop. Gone. Now what do I have left? I go this way. So we talk about as being bent. I have to play with that mole view, because it's not going to give you the right description on some of them, and I was hoping that you guys would have that as the way you could do molecules if you don't have a molecule set, because it's supposed to be angular right and based on formal charge, although it does have the disclaimer that when you go 2D to 3D it may not be correct. Okay. Excuse me. So now we have our lone pair up here, 2 bonding, 1 non-bonding, and that means our shape is bent. Now, and this is a common one, remember we did this, you're doing this for homework, kind of blowing up and giving you the answer. But this is SO2, it has resonance, and it's bent. Because it's bent, you no longer have the symmetry. If I go back to my molecule here, and I look at this molecule, there is no way that I can find 2 planes. I can get a plane here where I chop it in half this way and the 2 little atoms reflect on the other, but I really can't get another, like if I go this way, I should say I can go this way, right? But if I try to do other symmetry, you have a net pull. And basically what it is that, and it actually gets more than just doing the planes. And this is why for AP it gets a little more convoluted, because you have a net pull out towards the oxygen ends, because there's nothing offsetting like it was up here. When you looked at all the vectors, the physics vectors, they cancel out. But down here they don't cancel out, and this lone pair doesn't oppose the drifting out of the electrons in that direction. The electrons are moving towards the oxygen more than they are the sulfur. So we say the net vector, because there's nothing going upward, is this way. You have a net vector in the center down towards the bottom. Since there's a net pull, it is now polar. Okay? I know you're probably like, what? Again, we're going to work with this for the next 2 to 3 days. So it's not like, oh, here it is, and there you go. We work with it. Now we're going on to 4 faces. So 4 faces meaning tetrahedral. Okay? So I'm going to blow this up so we can work with it. Because every time, guys, that I try to do the video with just writing on it with the video software, a lot of people say that when you're watching it at home, the video is too small. And so I use the snip screen and expand it. So you have 4 faces, 4 domains. That's the word tetra. Notice the one above was tri. That's why some people say trigonal. I just say trigonal. If you have no lone pairs, you have that tetrahedral, which I showed you in the mole view, and which you see in the little, I'm getting out my little molecule set so that you can really see that. 1, 2, 3, 4. I'm not using the proper bond lengths. When you get into chemistry, there's always a certain bond length, whether you're single or double. I'm going to use the flexible bonds here rather than the short rigid ones. I can pull them out easier. Although some of these little molecules, if you're in school, and Richard, you have yours, put your name on it. The carbons aren't drilled right, and they're supposed to be drilled so that your little bonds go into them and that they're drilled at exactly the right angle. So if we look at our little molecule this way, here's my tetrahedral, 4 faces, 1, 2, 3, and then the bottom 4. Okay, so there's 4 faces as you rotate that around. And I hate the fact that there's so much glare from the lights. It kind of ruins everything every time I try to do something. Now that 4 bonding, 0 non-bonding. We take 1 off. This becomes a lone pair, and you can do this with this one. You can put 4 in here, but you got to make sure that you kind of put it at angles, and they would be like this to start, to give you that tetrahedral. Like it should sit, and maybe a large marshmallow isn't the best choice because it's really squishy. So my little bonds don't stay in place. But it sets, and then if you take the top one off, then you've got your trigonal pyramidal. If I take the next one off and I go 2 bonding, 2 non-bonding, right? Non-bonding would one be here, one would be there. Now I have bent. Okay, so bent in trigonal pyramidal, come on, it really doesn't want to go into that one. Are all polar. Okay, so on a tetrahedral, you do have equal and opposite pole if all 4 things are equal. Okay, so that's the thing. If you substitute in anything, it becomes unequal. Even if you substitute 2 in, it looks like there's symmetry, but there technically isn't, because remember, we're dealing with vectors. Okay, so if I have a carbon, and why aren't you drawing? Oh, yeah. I have a carbon, and I have a hydrogen going this way, and a hydrogen going that way. And you might say, well, I'm just going to draw, and I'm going to do 2 fluorines. I'm just going to draw the fluorine out like this, but you can't. It's 3-dimensional, so a fluorine's going to come out at you, and then a fluorine's going to go back into the computer face that I'm drawing on. Now, if you look at that, I can have a plane this way, cutting through the hydrogens. I can have a plane this way, cutting through the fluorines. I can't have a plane this way horizontally. This doesn't work. The fluorine will not reflect up to the fluorine. So if I make this for you, and I'm going to take 2 hydrogens off and I'm going to put 2 fluorines on, you can use 2 raisins versus 2 little mini marshmallows. Not that I'm saying that everybody has these at home, like has the type of food at home, But if you really want to play with it, that's one way to play with it. So here's my molecule, right? Here's the 2 hydrogens, they're white. Here's the 2 fluorines, they're green. Yes, I can have a plane that goes this way. I can have a plane that goes this way. But I don't have a plane that goes this way. I don't. You might say, oh, but if you rotate it really far around, you would do it this way. Well, that's kind of the same as doing this way and this way like I did before. All I've done is rotated and looked at it at a different angle. I don't have anything perpendicular to it. I'm trying to block the glare, so now that's not ideal. That's okay. So I can't go this way. Nothing works this way. It doesn't cut it to give you the symmetry. If I try to do this one in the mole view, which we should be able to do, I'm going to do the carbon-hydrogen bonds. And I'll do 4 singles. Okay, so I want that to be carbon, please. I'm going to change 2 of them to fluorine. I'll make sure these 2 are hydrogen. And I'm going to do my 2D to 3D. Now you can rotate it if you're in mole view, and you can see you really can't get certain planes to exist. It's almost like they lock certain things. I can get it going from you through the computer here, from you through the computer here, but if I rotate it like that, there is no plane to go across horizontally. Okay, so that has a net pull towards the fluorine. So as soon as you replace one of these, you are no longer nonpolar, right? So this is key in trying, when we do the lab, you got to remember that. Take one off, I get that trigonal pyramidal shape that I showed you. The one that they use a lot is NH3 and sometimes PH3, right? So if you're not good at figuring them out, remember, NH3 is trigonal pyramidal. Now its bond angle is going to be different, and you're going to have a lower bonding angle than this starting one. A lot of times I'll just tell you, you just say that it's less than 109 because of the electron pair repulsion, right? This has got repulsion, and it pushes the bonds together. And then if you take off another one, you got more electron pair repulsion, so this angle gets smaller because you're pushing those 2 together, and that is bent. Now this is the thing that really irritated me with the gentleman who did it for AP board. Right? He started talking about proper Lewis dot. Yes, this is a proper Lewis dot, but it is not really acceptable, because when you finish, you should be drawing water like that, because you should always adjust for the geometry. And he did not. He goes, oh, fill your empty spaces, here you go, and this is how we do the water, but this is how you should be drawing it. Always. Don't draw it the other way. Because if water is linear, you have no dipole, and water has a huge dipole, meaning polarity in 2 directions, right? Huge. The electrons flow this way, very much to oxygen. Electrons flow that way, very much to oxygen. That means this has a partial positive. It acts almost like it's bare and doesn't have electrons. That's what water has, all the properties that it has. You take that away and you draw it linearly, water doesn't behave like water. Just a little, I don't know what you would call it, bone to pick. I don't know why they did that, because that was just not a good idea. Okay, so that's your 4th domain. I think that's where I'm going to stop for this one, so you can start thinking about drawing structures.